All right, let's talk about surface integrals, but instead for scalar functions, we're going to talk about surface surface integrals of vector fields of a vector field. There we go. And the formula for this is just written as so. So we have a double integral bounded by our surface, dotted with our surface differential. But this is not the actual useful formula. This is just a general formula. The actual useful one that you'll be using is your vector field parameterized by u and v, dotted with the cross product of your parameterized partials, partial derivatives, dA, of your region. So this guy right here is going to be the actual useful formula. You're not finding the magnitude, remember this. You are not finding the magnitude of your vector field. You are just finding the cross product, and just leave it as so. So you dot product your parameterized vector field with your cross product, and you should get out a scalar function that you can actually integrate. Now, a surface integral for a vector field just calculates flux. So it calculates flux. Now, for the rest of this video, you're going to see on the top right some formula that says circulation. I wrote that wrong, and I noticed that after looking in my notes, and I corrected myself. So just keep in mind that it's going to be the calculation for flux, not circulation. And if I say circulation for the rest of this video, it's just a mistake. So for this problem here, we have a surface and we have our region that we're bounded by. So let's just quickly draw the region that we are bounded by. And the bounds of your region are just the bounds for your integral. So if I were to draw this out, let's label the x, y axis. If I were to draw this out, we're bounded by point 0, 0, and of course it's oriented in the counterclockwise direction at 2, 0, and 0, 2. Let's actually make this a little bigger so it's easier to see. So this is 0, 2, and this is 2, 0, and we have a triangle as our region. So this triangle as our region is the bounds of our integral for x and y. Now I should be using uv. Let's change this to uv because that's what our formula gives in the parameterization. So I'll use uv instead because that's actually the, I guess, less confusing. You don't have to confuse the variables x and y. So we have our little triangle drawn here, and now we just need to find our parameterization. So parameterization for any explicitly defined function is just like so. So we have uv is equal to, well, x is just u, v will be y, and z component of your vector field is just equal to this function here. Z is equal to 4 minus x, and you can replace x with u and v with y. Therefore, this is our parameterization for our function. Now, what we have to do is find the u partial, not x. I'm instinctively writing x. We have to find the u partial. So the u partial for this is just 0, 1, negative 1, and the v partial is just 0, 1, and negative 1. If I were to find the cross products of these two, you would get 1, 1, and 1. So this is your cross product in this part of the surface integral calculation. So we found the cross product between u partial and the v partial, and then we get this guy right here. Perfect. Now we have to parameterize our vector field. So what is our vector field equal to in terms of u and v? Well, we have x right here. So x is just u in our parameterization. We have y here. Y is just v. And we have z here. And z is 4 minus u minus v in our parameterization. So this is our vector field. And all I have to do is just set up your integral. So we'll mark the region. So it's your vector field parameterized. So we have u v 4 minus u minus v dotted with your cross product, which is just 1, 1, and 1 of dA. Now, all we have to do is find our bounds and solve for this dot product. Well, solving for this dot product is easy. Everything is just multiplied by 1 and you add it together. So you have 4 minus u minus v du dv. And these terms cancel out. So all you're left with is a double integral of just 4 as the integrand. Now we have to find our bounds. Let's write dv du actually. Let's write dv du. Let's set this to dA. And I'll show you the reason why actually. So our bounds is bounded by a function at the top. So this triangle is bounded by a function. So we need to write a function for this, and the function for this is 2 minus u. And the second bound, or the bottom bound in the v-axis is just 0. And u is bounded by 0 and 2. So our bounds for v are 0 and 2 minus u. And our bounds for u are 0 and 2, written down in blue. So if we were to just solve this integral, you get 8 minus 4u. And if you were to solve for this integral, 8 minus 4u of du, you'd get 8u minus 2u squared from 0 to 2, which is just 8. So 8 is the answer for this integral. For this problem, you are already given a parameterization, so that'll make everything a lot easier. And because you're already given a parameterization, and we also have our bounds for u and v here, and our vector field, well, what do we do? Well, first thing I'm going to do is find the cross product. So let's find r of u. R of u is equal to 1, 0, and 1. And r of v is equal to 0, 1, 0. 0, 1, 1, sorry. If you were to find the cross product of this, you'd get, let's put the cross product in green. If you find the cross product of this, you would get negative 1, negative 1, 1. So we have a cross product here. And all we need to do is parameterize our vector field. So let's parameterize that. So our vector field is defined by y and z. So y in our parameterization is just v. And z is uv. So uv. And x is just u. And z is, again, u plus v. And xy is just u times v. So this is our new vector field here, parameterized, given by our parameterization. And if you just want to expand this a little bit, make this a little easier to understand, we have v squared, u squared plus uv, and uv stays the same. Hold on, I gotta remove this dot here, it's kind of bugging me. This little thing right here. Okay, now that we have that, we just dot product our vector field with our normal vector, which is simply just our cross product. And what we get is negative uv minus v squared minus u squared minus uv plus uv. And these terms cancel out. So our integrand is just this guy right here. So our integrand for our double integral is just we can factor out the negative. So we have uv plus v squared plus u squared. 0, 1, and 0. And 1 are our bounds that are already given. And this is du dv. It doesn't matter what order we write it because the bounds are the same. So let's solve for this integral. First thing we're doing, solving for the u in terms of u. So we have, I'll put the negative in a blue box because it is important. Let's not forget about the negative when we're solving it, but we're just going to omit it for now. So we have uv v squared plus u squared du. Let's write the d better. And the integral for this is just u squared times v over 2 plus v squared times u plus u to the power of 3 over 3. And our bounds are 0 and 1. If we just plug in 1 for all this, we just end up with v over 2 plus v squared plus 1 over 3. So this is our new integrand. And then all we have to do is solve for this with respect to v. So v squared 1 over 3 dv. And the integral of this is v squared over 4 plus v to the power of 3 over 3 plus v over 3. And the bounds are just 1 and 0. So we plug everything in, we get 1/4 plus 1 over 3 plus 1 over 3, which is equal to 11 over 12. But don't forget the negative symbol with the minus, and let's write minus here in blue. So this right here is our answer for this integral. So if you guys have any questions, put it down in the comment section.